Okay, so welcome to class today. Today will be a work day. I'm just going to introduce the next project. I have posted this on Canvas. So this is actually going to be the last project, but there will be an extra credit project for those who want the extra points after this one. So this is the last required project for the class. However, if you want to either do something cool or need some extra points for your grade, you can do the extra credit project, which will be due the last day of class, which is August 11th. But for this project, we're going to change gears a little bit. So what we've done so far, the entire class has been the heat equation, solving a heat plate. We've done domain decompositions. We've done OpenMP. But now we're going to do something called what's known as the n-body problem. And the n-body problem is actually extremely prevalent in the computational sciences. When we're talking about galaxies and stars, you know, every single star has an influence on every other star. And so it's called an n-body problem because there's n bodies and they're interacting with each other. And if you have n bodies, then you're going to have n squared computations that have to be performed. So every time you double the number of bodies, you quadruple the number of calculations, which means it can be very hard to scale these kinds of simulations up. Now, I'm going to detail a very basic way to do this. It's the way we're going to do it. I want you to know, however, in my research, I've never actually done an n-body problem. I've been spending the last couple of weeks researching it. In real life, you should never do this on your own. Okay? You should use someone else's code. But the basic idea here is that we have a body. It's governed by Newton's third law, of course, ignoring relativity. The force equals the mass times the acceleration. So in the case of gravity, the force vector is determined by this equation here. The mass of body I, the mass of body J, the gravitational constant, the radius, the distance between the two bodies, and then the direction vector here. Notice I put in a small epsilon factor. That is for numerical reasons. There are other ways to do this, but this is the easiest. It prevents divide by zero errors, because what if the two bodies are coming towards each other and they end up on top of each other? That would be really bad. And since we're doing non-collision in this case, I mean, if you want to, you could code up a collision so that they merge into one object, but then you have to conserve momentum, and then your parallelness gets all screwed up. So we're not going to do that. We're just going to throw an epsilon in there and call it good. So now we can simplify the number of calculations by using Newton's second law by saying that Fji is equal to the negative of Fij. So we only have to perform half the number of computations, which is good. And then to get the total force on a body, obviously we just sum everything up. And we get the total force on the body. From there we can calculate the acceleration, the velocity, the position, etc. So now the numerical method. So to solve this, we're going to take the second order ODE and break it into two first order ODEs. So here's the first one where we say force divided by the mass is equal to the acceleration. Well, that's just the derivative of velocity, whereas velocity is equal to the derivative of position. And we are going to solve this two equation system using what's known as leapfrog integration or Verlet integration, I think is how you pronounce it. And there's actually a few different ways to structure this, but I kind of figure this is the easiest way. So the new position, r at k plus 1, is equal to the current position, plus then the velocity times the delta t, the time step, and then we do half of the current acceleration vector times delta t squared. And what's funny is this looks an awful lot like the parabolic trajectory equation from high school physics. Remember? I just thought that was a nifty coincidence. Anyway, and then to calculate the next velocity time step, we are going to use the current velocity, and then we're going to basically take an average of the current acceleration and the next acceleration, which means in between solving these two equations, we have to calculate the new acceleration. Does that make sense? In order to get this term here. So we update to the new position, and since the acceleration is only dependent on where everything is located in this situation, we can do that. Now the reason we're doing this is a second order method. If you just did an Euler method, it sucks, so we're not going to do that. But also it is a symplectic integrator, which means it conserves the energy of the system. A lot of numerical integration techniques don't do that. And in a lot of cases it doesn't matter, but in this case it's very important for orbital mechanics. Okay, so now we're going to talk about how we actually parallelize this. So if you have a region of space, okay, and you've got some planets inside of it, how are you going to parallelize this? I mean, you could read the screen right now, but just think about it. Could you do domain decomposition? If you have a region of space with some planets in it, could you do domain decomposition?
What I'm thinking is you make a directed graph of the relationships between the planets, and then you have it basically a 2x2.
Okay. That would be, I think that's more similar to the tree-based methods, is what you're suggesting. I didn't research those because they looked really complicated.
Spatial decomposition doesn't really make a whole lot of sense here because we don't know where the bodies are going to be.
Exactly. We don't know where they're going to be. And so one processor could have 0 planets, while another processor could have all the planets. So in this case, what we're going to do is we're actually going to split the planets up. Each processor is going to own a given set of bodies. And so then the question is, how are we going to actually share information between the processors? Because every single processor needs to know where all the other bodies are, right? So how do we go about doing that? So the answer is we're going to do a ring shift. Okay, so these diagrams take a little explaining, but each one of these squares is a processor, okay? And so processor 0, that's the one we're looking at. He owns, say, 10 bodies. All the processors own 10 bodies. And he can compute the forces between all the 10 bodies that he has easily, right? Shouldn't be too big of a deal. And then what he does is he takes his 10 bodies and passes them to the right, while he receives number 7's 10 bodies. And then he computes the forces of number 7's bodies on his bodies. And then they all pass again. And then they all pass again. And then they all pass again. And so that's what this is showing here. Step 1 is compute local forces, okay, based on the body's positions of processor 0. And then step 2 is to compute the forces, again, between bodies from processor 0 and bodies from processor 7. I see some quizzical looks.
Okay, so each processor is going to have two separate arrays. It's the bodies that it owns and the bodies that's computing against.
Right, and I call those the visiting bodies.
Okay.
Okay, because they are visiting, and then they're going to get passed on. Does that make sense? So once everyone makes it all the way around, everybody has seen all the bodies and have been able to compute all the forces. And that's what I made up this term. That's what I'm calling a full ring shift, because it goes all the way around the ring. Okay. However, this approach does not take advantage of Newton's second law. Okay. So there's another way to do it, which is the half ring shift. And in this case, you don't just send the bodies, but you also send a complementary force array along with the bodies. Okay, and so that's what I have detailed here, is that we set the processor 0, he sets his complementary force array to 0, and he passes his bodies to processor 1. Processor 1 then computes the forces from R0 and R1, but then also puts the negative of that into the little f array here. Okay, while at the same time, processor 0, he's handling bodies from 7, 6, 5, and 4, while his little red one handles 1, 2, and 3. Okay, and so that's a half ring shift. Everything gets turned halfway, and then they all send the little f arrays back to where they came from. At which point the last step is to add the two force arrays together. Does that make sense?
How does kind of
Kind of. So the red is what I'm calling the complementary forces. I don't know if that's the right term or not. Maybe anti-symmetric forces, but so the particles, the bodies, don't make it all the way around. They only go halfway. At which point all the computation stops because we've now computed everything that we need to.
So we're basically just going for the net force on each body. And
Exactly.
we don't care how we get it, and so we just say, hey, I'll compute half of them. Here's the rest. You guys compute it for me and give it to me later.
Exactly. Yes. So, yeah, exactly what you said. I'm going to compute the left half of the circle, and then everyone else is going to compute the right half of the circle for me. And we can't go to 4 because then we'd get duplicate calculations. So that's something to watch out for as well. Make sense?
Yes and no. So I get the concept, but the red only does 3 shifts, while
Yeah, so it can't do another shift because there's an even number of processors. So if we did another shift, then actually I numbered these. So step 1 and 1 here are the same. Step 2 and 2 are happening at the same time. 3 and 3. So this red goes all the way up to 4, and then there's a 5th extra step here. So there is an extra shift in there, but it doesn't compute the complementary forces on that last step. Does that make sense?
yeah. So it doesn't really matter if we do a red shift or a black shift. We just need to do one, but not the other.
Yeah, exactly. Okay, so that's how we do this in parallel. Now I've written down a general algorithm how to do this. Okay. Basic idea here is we're going to do what's called a cold start. We're just going to generate a bunch of random bodies. Okay. And all the initial velocities of these bodies are going to be set to 0. Okay. And then, so this is a pretty difficult problem. I've wrote down this for a half ring shift. Okay. And then a full ring shift would omit certain parts of the algorithm. But your assignment is to write a code to solve the n-body problem using MPI in 2 dimensions. Okay? We're not doing 3 dimensions. We're going to set the gravitational constant equal to 1, delta t of 0.001, and epsilon of 10 to the negative 6. For each run, take a total of 1,000 time steps. Perform a weak scaling study of the code. So I want you to run this with 1 processor, 8, 16, and 32. Okay. So when you're doing 1 processor, actually I forgot to change that number. That number needs to be 2,500. I'll change that and repost this. Okay. Because I actually haven't gotten around to the MPI part yet. I only got this working in serial. So, and these bodies are going to be uniformly distributed in the region of space from -1 to 1. So, nice little square. And all the bodies should have a mass of 1. See what I'm doing here? Simplifications. Go find them.
Randomly or uniformly distributed?
So a uniform random distribution. Yes. And you can see an example of that in the Pi integrator that I've posted in the lecture notes on Canvas. So when performing the weak scaling study, each processor should randomly generate an equal number of bodies. And of course, since the amount of work done is actually proportional to n squared, the total number of bodies should scale proportional to the square root of the number of processors, like we've done before, just with bodies instead of cells. And then also the region in which the bodies are generated should also grow proportionally to the number of processors in order to provide a constant body density. And so the initial region is going to be this right here. So we have negative n processors to the 4th power, or to the 1/4 power.
Go proportionally to n pros or n bodies?
N processors.
Okay.
Yeah, because n bodies is also scaling by that much. So it works out, I promise. I just barely did it. So again, I want you to submit a tarball which contains your code and a makefile with the usual 3 targets, and run, which will run your program with 4 processors. And then I want you to provide a PDF report which contains a plot of the weak scaling results compared against Gustafson's law and your estimate for the serial fraction of your code. Okay. Now, if you do the full ring shift, grading will be based on a 100-point scale. However, if you do the half ring shift, I'll give you 10 extra points. Okay. So, you can do whichever one you want. I'm fine with either one. So yeah, that's the next project. It's going to be due July 3rd. And this is the last July 3rd, 23rd. Sorry. July 23rd. I can read. So anyway, this is the last official project. There will be one more extra credit project after this one. So anyway, that's what I've got for you. Any questions? Okay. Sounds good. And just as a demonstration, I want to show everybody. No! There's more things to install. It's like, seriously, Matplotlib, if you need it, just download it. Okay, well, that was fast. Here's my end body problem.
They're all collapsing in each other.
Yeah, so they're all collapsing in on each other. And then they all explode due to numerical errors, and this is why we don't do it ourselves. But it gets the basic idea. And in fact, what?
If you don't do friction collisions, they will
Right.
Should it collapse again, yeah? Or no?
They don't actually. Well, I mean, I'm only running this for 1 second.
But if you kept running it, they probably would.
Not necessarily. Orbital dynamics is actually a really tricky subject. And sometimes we can spot some binary systems. Yeah, these guys are slowly orbiting each other. There's another one right there, except it just got broken apart by another body flying past it. So anyway, I've posted this Python file in the Project 7 folder as well. It may need a little tweaking, so let me know if you can't get it to work. But so you can use this to debug. And a good way to debug your code is to just run a two-body problem. Okay, and you fix the first guy at 0, 0, and then the second guy you want him, give him a starting velocity, and he should orbit the first one if you just fix the first guy so he doesn't move. So that's a good way to debug as well. Anyway, so this is probably one of the coolest things I've ever made. Anyway, that's what I have for you today, so we'll work for the rest of the time.